Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 57. It's on entropy, which is really the dispersal of matter and energy. So imagine I had a little bit of milk in a glass and I were to spill it. I will have increased the entropy of this isolated system. And there's an old saying that you shouldn't cry over spilled milk. I totally disagree with this. You should cry over spilled milk. And the reason why is it's an irreversible process. In other words, it's not just going to magically move back into the glass. You've increased the entropy and it's going to take a lot of work to put it back where it was. And so entropy in AP chemistry is not something that you'll have to calculate. You have to understand it qualitatively. In other words, you have to look at a system and figure out what's happening to delta S. And so what is delta S? That's simply the change in entropy over time. Now, what does this little degree symbol stand for? That means that we're measuring it at standard temperature and pressure. And so if we were to look at a system, we should be able to make predictions about what's happening to our delta S. And that's what I hope you can do at the end of this. And so if we define it, it's simply dispersal. Dispersal of matter and dispersal of energy. So what are some examples of that? Let's say we were to make some phase changes. We were to go from a solid to a liquid to a gas. What would we be doing? We'd be dispersing or moving that matter away from its center point, and so we'd be increasing the entropy. In other words, our delta S would be a positive value. We'd make that matter dispersed over time. We also could do that by stoichiometry. In other words, if I look at the moles before a chemical reaction and the moles after, if I have more moles after the reaction, I've increased the entropy. And also, if we take a gas and we increase its volume, we're moving those molecules apart, and so we're increasing entropy, or delta S is going to be a positive value. Now, let's say we look at energy. How could we disperse energy? Well, by increasing temperature. If we increase temperature of gas, according to the kinetic molecular theory, we're spreading that energy out and we're increasing entropy. Now, entropy is a term that people really struggle with, and so I wanted to start with a good example. And so I've got two videos here, but they're the same exact video. It's just that one of them is played forward and the other is played backward. And so your goal is to figure out which one is forward. So let me start playing that. It's just going to loop over and over and over again. And so your goal is to figure out which one is forward. Have you decided yet? The right answer is A, but that was kind of hard. Let's look at another one. I've got a little pendulum here, and let me play this video. Again, it's the same video clip. It's just that one of them is played forward, and the other is the same clip. It's just played backward. Have you figured out which one is forward? There's some clues in here, but the right answer is B. Let's look at the next one. It should be a little easier now. So if we look at the next one, I'm going to play this again. So again, same video. One is forward, one is backward. Hopefully you've figured this out. The right answer is B is being played forward, and A seems somewhat magical. It's being played in reverse. Let's look at the milk. So if we look at the milk right here, which one is being played forward? Hopefully you've figured this out. A is being played forward. Okay, and so why did I do that? Well, what we're looking at here are irreversible processes. In other words, if we play it in this direction, it's irreversible. In other words, it's impossible for it to occur in the reverse. Now, it's not totally impossible. That could occur, but it's statistically improbable that it's going to move in the other direction. And so that direction is really important when we start to talk about entropy. Because what happens during an irreversible process is that we're increasing the entropy or the dispersal of that system. And it just doesn't move back, and that'll become really important as we talk about the next few videos. And so the second law of thermodynamics says that in an isolated system, or a closed system isolated from the universe, entropy never decreases. In other words, our delta S is always going to be positive. In other words, matter and energy are going to become dispersed over time. In other words, randomness increases over time. Now, you might think to yourself, I know that's not true because I see stuff out there that's not random. In other words, I see trees and cars and DNA, and I know these things have a high amount of order. Well, you're not violating the second law of thermodynamics because remember, we're talking about an isolated system. And so we can decrease entropy in an isolated system, but as we do that, we're increasing entropy of the surroundings or the universe around it. And so again, to define entropy, what is it? It's simply matter dispersal or matter spreading apart. And so let me give you an example of a certain type of matter dispersal would simply be phase change. So as we move from a solid to a liquid to a gas to a plasma, that matter is moving farther apart. And so as it's doing that, what we're doing as we move from a solid to a liquid to a gas is that matter is spreading apart. And as it does, we're getting a delta S, which is going to be a positive value. Now let's look at stoichiometry. You should be able to look at an equation like this and immediately figure out what's our delta S. Well, how do you do that? So if we've got our reactants on the left side and our products on the right side, we have 2 moles on the right side and only 1 mole on the left side. If we show you a picture of that, it looks like this. So we have dinitrogen tetroxide and we're making 2 moles of nitrogen dioxide. And so what are we doing? We're increasing the entropy. You try the next one. So if this is our equation, so we're taking liquid water and turning it into gas, hydrogen gas and oxygen gas. What's happened to the number of moles? Well, we've increased that. So our delta S is going to be a positive value. We're spreading that matter apart. Now there's another clue here as well. We're going from a liquid to gases, and so we really are increasing the entropy of this system. Now let's look at gas volume. As we increase the volume of a gas, so if we have a known quantity of that gas, as the volume gets larger and larger and larger, the matter is spreading apart, and so we're going to have a delta S that's going to be a positive value. So not only is entropy dispersal of matter, it's also dispersal of energy. So if we were to look at this Maxwell-Boltzmann distribution of a gas, what we would see is a curve that looks like that. In other words, these are going to be the number of molecules on the left. This is going to be their energy. You can see that some of them are going to have a high amount of kinetic energy. Some of them are going to be lower. But if we increase the temperature, what does that curve look like? It's shifting everything over to the right side. So we're going to have more molecules that have a higher amount of energy. And so what's that doing to our entropy? It's increasing the entropy because we are increasing the dispersal of that energy. And so did you learn to predict the sign and relative magnitude of entropy changes associated with chemical and physical processes? Could you remember this one right here? I hope so, and I hope that was helpful.